Alright, so I got that recording. Let me get the online homework open. There was probably a couple that were a little bit trickier than the ones we did in class for examples.
Yeah, I think number 10 was a little bit
One of the trickier ones? Okay.
Yeah, number 9.
So my math lab 4.1, so we'll start with 9 and 10. Waiting on the internet.
Have you?
Okay, I might have to try the staff email here. Or the staff internet. Now, when I do some of these problems, the functions are going to be of the same form, but they might change like what the coefficients are, so they won't exactly be everybody's not going to necessarily have the same numbers, so we're going to be going off my numbers. Okay, so number 9 was about intervals of increase, decrease in the local extrema, i.e. local max and mins. So my function on number 9 was f of x equals, and I have x minus 8 times e to the minus 2x. Okay, and then we want intervals of increase, decrease, and local maximums and minimums. Ignore that. That's not McDonald's. I swear. It totally is. Okay. Okay, good. Desmos works, because I'm going to try and use the projector today. Hopefully it'll let me. Okay, so remember we're in section 4.1, so we're just looking at what the first derivative tells us. So we don't have to worry about the concavity and inflection points at this moment. So we're just going to take a derivative f prime. And then to do that, we have to use the product rule. So we've got to find a first function. I just like using the x minus 8 as the first, and the e to the minus 2x as the second function. And what we do is we do the first function times the derivative of the second, which is the same thing, times the derivative of the exponent. So remember, I'm using that property d over dx, e to the f of x is e to the f of x times f prime of x. Okay, so derivative of exponential base e is the same function times the derivative of the exponent. Then you're going to do plus the second function, e to the minus 2x, times the derivative of the first, but the derivative of x minus 8 is just positive 1. Right? You can always think of this is a linear function with slope positive 1. So its derivative would be that. Okay. And then now's that point, and this is why the homework certainly made you do all the simplifying your derivatives. It was for this stuff in section 4.1 and 4.2, just getting us ready. So now I can try and factor anything out of both of these terms that are in common. Right? So this is the first term, that's the second term. Anybody see any common expression in those?
E to the negative 2x.
Okay, so they both have an e to the minus 2x, so you can factor that out front. The leftover stuff is going to be negative 2 times x minus 8, because we just factored out this e to the minus 2x, and then I only factored out the e to the minus 2x over here, so you still have a plus 1. All right, and then you can clean up the inside a little bit. You're going to get a minus 2 times x, so you get a minus 2x. Negative 2 times negative 8 is 16, but then you have a plus 1. So you get a minus 2x plus 17. I should have brought something to drink. Okay, so we took a derivative with product rule. Both terms had an e to the minus 2x. We factored that out. We figured out the leftover terms, and then we simplified that to minus 2x plus 17. And now you want to find out where this is equal to 0 or undefined, because you got to find your partition numbers. The partition numbers will tell you at least where the sign on the derivative might change from positive to negative. If the partition numbers are also critical numbers and the derivative changes sign, that gives us the local max and mins. Now, you should always maybe be thinking of this. You should maybe be trying to think of the domain of the original function. The domain of x minus 8 is all real numbers, and any exponential function has domain all real numbers. Okay, so the domain of the original function is all reals. And also, what's the domain of the derivative going to be? That is also all real numbers, because the exponential is defined everywhere, and this linear is defined everywhere. Okay, so we just need to figure out where the derivative equals 0, because it's defined everywhere. Scott, you need one of these handouts from yesterday? Right now we're just going through homework problems though, so we'll pick up on where we left off shortly in just a minute. Okay, so what this implies is that whenever you have a product of two things equaling 0, either the first term is 0 or the second term is equal to 0. Now, the graph of e to the minus 2x, I could graph this on Desmos or something, but it's a decreasing exponential function. But notice the graph is always going to be above the x-axis. So actually, it turns out that this doesn't have any solutions. Okay, so this one essentially crosses off. We don't need to solve that because the graph of any exponential that has a positive coefficient is always going to be above the x-axis. It'll never cross the horizontal axis. So it'll never be 0. So the only critical numbers are going to come from the second equation. And when you solve this one, you get x is equal to 17 halves. Or, I believe, if you like the decimal, that is 8.5. Okay, this is the only critical number. It's also the only partition number, but it happens to be in the domain, so it's a critical number. So now what are you going to do? You're going to form your number line. So this is the sign chart for the derivative. You can put your 8.5 on it, and then you're going to test values. So remember f prime of x, we already found it. It was e to the minus 2x times minus 2x plus 17. The e to the minus 2x is always positive, right? So this term is always positive, so the sign is completely determined by this linear factor. If we plug something less than 8.5 in, I believe like we can use 0 as a test value. Negative 2 times 0 plus 17 is positive. So to the left of 8.5, the function would be going up or increasing. And then what happens if you plug something bigger than 8.5 in? Again, this will always be positive. All you said it would become negative.
Yeah.
Right? Even you could use 100 as your test value.
Well, I was thinking about just 9.
9 would work too, right? Because negative 2 times 9 is minus 18 plus 17 would be negative. Okay, so I'm kind of skipping that part where I do it more carefully and write the table and pick my test values. Okay, but the derivative is positive to the left of 8.5 and negative to the right of 8.5. Okay, so, again, I don't really like pointing this thing over to the left, but we'll do it right here. We'll say f is, so you can say f is increasing on what interval? So remember the domain is all real numbers.
Negative infinity to 8.5.
Yep. F is decreasing on the interval from 8.5 to infinity. So that'll give you the first part of the question. Okay, and then I got to make some room for this next part. So now that I'm done with the derivative and I've made my sign chart, I just have to determine if I have any local max or mins. So what do you think? 8.5 is a critical number, and the derivative does what when you cross 8.5?
Well,
It changes signs, right? So you can think about it this way. To the left of 8.5, the function would be increasing, and then you'll hit a local maximum, and then the function changes to decreasing. Now that's not really what the graph is going to look like. I'm just emphasizing that we're increasing to the left and decreasing to the right. So you have a local max at x equals 8.5 of, and you plug it into the original function to get the maximum itself. And then let me see what they want for an answer here. If I can find where the homework part is. Oh, they want you to use fractions for, so I have to go back to 17 halves. All right, they like my interval of increase. They like my interval of decrease. And the function has a local maximum, no local minimum, and you'd have to plug that 8.5 into the original function. This is going to be 8.5 minus 8 is going to be 0.5 times e to the negative 2 times 8.5, I believe, is going to be minus 19. And they want you to round to 4 decimal places.
It's just 0.000.
Is it really?
Yeah, there's a 3 at the end, but there's more important.
Yeah. So essentially the local maximum is 0 and they like it. Okay. And then yes, good. I was hoping that people would ask about this one. So again, number 10. Is everybody okay on this one? Okay. So number 10, everybody's going to have different coefficients and different powers, but hopefully you can just take the numbers I have and kind of just modify your problem a little bit. Is everyone okay if I erase this, or I can wait a minute if anyone still needs it? Okay. So number 10, I think it's the same question. Intervals of increase, decrease, and then local extrema. And they give me f of x equals 3x to the 2/11. And again, some of you have different powers. Reed, you had like 4/7 yesterday and a 3/7 or something like that. And then it was minus x to the 3/11. So some of you are going to have different powers. Okay, but I think if you just write this down and kind of follow the steps and use the same ideas, you should be able to get to the right answer. Okay, so now we do our first derivative test analysis. So we have to take the first derivative. We're just going to have to use the power rule, and we can take the derivative term by term. The first one's going to be 3 times 2/11 x2. You subtract 1 from that. I believe you get minus 9/11.
I put it in my calculator. Oh wait, never mind. Yeah, you're
See
right.
what it, okay. Yeah, because I think if you take 2/11 minus 11/11, you get negative 9/11, and this will be minus 3/11 x to the, I believe that'll be minus 8/11. Now you have to simplify this thing. Okay. So again, this is why it's good the homework forced you to simplify it, getting you ready for this part of the text. Now I can factor out common factors. Notice that there's a 3/11 in both terms. So the 3/11 can come out front. And then you have 2 powers of x, but you always factor out the one with the smaller power, right? The one that has the least power. I believe negative 9/11 is less than negative 8/11. So you can factor out x to the minus 9/11. So both terms had a 3/11. And then I factor out x to the lower power, minus 9/11. So I already factored out this. I factored out the 3/11. The first term just has a 2 left. And we factored that 3/11 out, so minus, I don't need the 1. It's minus x to a power.
I think.
Didn't you figure out the extra both?
Yeah, but only this x goes away because I literally factored this x to the minus 9/11 out. But if I factor x to the negative 9/11 out of this, there will still be x to a power left over. Right? It's just like when you do x squared minus x cubed.
Oh, okay.
Right? You can factor out an x squared, and that's gone in the first term, but there's still some power of x in the second term. Okay. Similar idea, it's just with fractional exponents. Now, when you distribute this back through, you're going to add the powers. And I need to do minus 9/11 plus something to get minus 8/11.
I think in the example they actually took out the negative 8/11 and left the negative 1/11 power.
They might have, but you're going to get if I pull the minus 8/11 out of this, I'm going to still have negative exponents. And it's fine, you can do that. You're going to get the same thing I get. It's just factoring in a different way.
Okay.
So, but this will still be 1/11. Okay, because I think minus 9/11 plus 1/11 will give you minus 8/11. But yeah, that'll work too. It's just, I'm in the habit of always factoring out the lower power.
Okay.
Okay. But not everything I do is going to be the same as what they do in the question help. There's more than one way to do these. And then now when you get rid of negative exponents, you're going to have 3 times 2 minus x to the 1/11th. And in the bottom, you're going to have 11x to the 9/11ths. Right, so I just moved this negative 9/11ths down with the 11 by changing the power to a positive. And then I just had 3 times this left in the numerator. Now, I think I can leave this domain up here. Because x, so whenever you have a fractional exponent, what's in the numerator, you would do x squared first and then take the 11th root. Okay? So since you're squaring first, and here you're taking a cube root first, or you're doing a cube power followed by an odd root, this technically has domain minus infinity to infinity. So now what we have to do here is figure out where this is 0 or undefined. Okay, so now we're trying to find our partition numbers. But since our domain is all real numbers, all of the partition numbers will also be critical numbers. I think it's easy to see. Anybody know what to do when you have a fraction? It's 0 when the numerator is 0, and it's undefined when the denominator is 0. Okay, so whenever your derivative is a quotient, to find your critical numbers, you just set the top and the bottom both equal to 0. I think it's easy to see it's undefined. You can't plug in 0 for x. Okay, again, that's an odd power followed by an odd root. You can plug anything you want into that. So the critical numbers are x equals 0, and then we'll find the other one by setting the 2 minus x to the 1/11th equal to 0. Right, so if I set the numerator equal to 0, you can divide by 3 on both sides, so you just have to figure out when this factor is 0. You can add the x to the 1/11th to the right. I will switch the order. And then anybody know the trick for how do I get rid of a fractional exponent? What power can I raise both sides to?
So the 11th.
Yeah, right, if you do, because when you raise a power to a power, you multiply the exponents. 1 over 11 times 11 would give me 1. So this implies the other critical number is 2 to the 11th, which I bet is giant, isn't it?
2048.
Oh, it's not as big as I think.
Well, I'll double check, but
That sounds about right.
Problem.
I think 2 to the 10th is 1020. Yeah.
You're doing the top equal to 0, right?
Yeah.
Why didn't you bring the 3 over?
Because the constant doesn't affect. If I set this equal to 0, 3 is never equal to 0, so this factor has to be equal to 0. How about, can I just show you? Just divide both sides by 3. And then 0 divided by 3 is still 0. Okay. So another way to think about it is 3 is never 0. That means this factor has to be 0. Or you could just set the whole thing equal to 0 and divide by 3. Yep. Is that okay if I erase this to make room for the sign chart? Okay, so now you have your critical numbers as 0 and 2048. So you can put your 0 and your 2048 on the number line. That number line represents the x-axis. And then you have to pick test values. I'll let everybody think about this. Well, this one might be a little harder to think of. If I plug something to the left of 0, so I might have to get my calculator out for this one. My arithmetic skills kind of stop at stuff like this because it's hard for me to see. So to the left of 0, you can plug, say, any negative number into the derivative. So I'll do fraction button, and I'll just plug -1 into this. So 3 times 2 minus -1 to the 1 over 11 power. And in the denominator, I will do 11 times -1 to the 9 over 11th power. So I get a negative number. Sorry, I didn't leave myself much room here, but so the derivative to the left of 0 is negative. If I plug something like positive 1 is a really easy test value, because 2 minus 1 is positive, 11 times 1 is positive, and 3 is positive. So if you plug in a positive number into the derivative, you get a positive, and then I'll let you check for yourself, but I think if you plug something bigger than 2048 in, it is going to switch back to a negative. But be careful, it isn't always going to be the case that it alternates every time. Right? You can have a critical number where the derivative stays the same sign. So make sure you are testing the intervals. Okay, so f is then increasing on 0 to 2048 and decreasing on 2 intervals. One is minus infinity to 0. And what would the other one be?
2048 to infinity.
Yep. Wherever your sign chart has a minus sign.
Yeah, actually the way you did it makes a lot more sense than the question out, because I was trying to figure out how to do the negative
factor and
fractional
stuff.
with exponent and multiply it by 2.
Yeah, it sounds like the way they did it, you'd have to do more algebra.
Yeah,
anyways.
but they skipped all the algebra and they just had x to the negative 1 over 11 equals 2.
Oh.
And they said that it was 2048. So.
Okay. Yeah, so I oftentimes wish I had the time to go and rewrite the question help, because a lot of times I read through the solutions and I'm just like, what the heck was this person thinking? So if you're, I don't have a problem if you want to come meet with me and I can show you how to work through the algebra too. So again, I set the derivative equal to, to figure out where the derivative is 0, that's where the top is 0. It's undefined when the bottom is 0, and we got 0 and 2048. We made a sign chart for the first derivative. So we put those critical or partition numbers on the number line. They just happen to be critical numbers this time. If you plug something negative in, the derivative will be negative. You plug something like positive 1 in, the derivative will be positive there. And if you plug anything bigger than 2048 into this, the derivative will again be negative. So you have 2 intervals of decrease and 1 interval of increase. And then what about local max and mins? I'll let you guys plug this stuff in your calculator, but is there going to be a local min?
Yeah.
So there's a local minimum of f of what value do you plug into the original function?
0.
Right, yep, at 0 you change from decreasing to increasing. So f of 0 would be the local min. That one's pretty easy to calculate, right? Both terms have an x, so you're going to get 0. And then you have a local max of the original function evaluated at what?
2048.
2048. And I will let you guys think. I don't think it's as important that I plug that into the function. Okay. But yeah, I mean, this is one of the reasons why earlier on in the class I said something along the lines of, it's not always, the calculus part is certainly a part of it, right? You have to know what the derivative tells us and interpret the calculus. But a lot of it comes down to algebra skills. Okay, so I think hopefully everybody got a lot of practice with the algebra, because the homework made you simplify all your derivatives. Okay, so we're not just doing this for the first time. So that's why I wanted to make you guys have to simplify everything on the homework. On the test, I was nice. I just wanted to know that you can apply the derivative rules. I wasn't as worried about the simplifying. But on the next test, you're going to be stuck simplifying just because you have to. I'll try and make things not too nasty and crazy on the tests, right? There's only so much time. I can't give you the problems where the algebra is as complicated as it can be. So I'll try and be generous on the test for understanding that there's time constraints. Okay, and I think that's about all I have time for to do from the homework. Again, for 1, there was no written homework, but I do have written homework for section 4.2. We can go over that on Thursday. So again, the plan is there's no official class meeting tomorrow. Whatever I don't finish on this handout, tomorrow morning I'm going to make a video and post it onto Canvas. And it'll probably only take me 20-30 minutes to finish, make a video. So just make sure you watch that before you come to class on Thursday. And then Thursday we're going to start something new. My guess is that the next section is about what's called optimization. So now we'll be using first and second derivatives to figure out what our maximum profit is. How do we maximize profit and revenue? How do we minimize our costs? Okay. All right. So hopefully when I get there, I'll be able to use Desmos, because there is one question where I'm going to have to use a graph. But first what we're going to do is we're going to talk about curve sketching techniques. So now I'm on page 3. So this is where we left off last time. Okay, so then there's a first version of this graphing strategy. We might actually do this more in depth later, we'll see. Okay, but there's kind of this procedure spelled out for us. So in example 4 and 5, we're going to sketch some graphs. Step 1 is always to analyze the original function. Right? So you're going to want to maybe find things like the domain. What are the x and y intercepts? So that's just getting as much information as you can from the original function. And usually it's just the domain and the intercepts. The intercepts will give you a couple points you have to pass through. And the domain's going to tell you where you need to graph. Okay? And then step 2, you do your analyzation of the first derivative. You find the intervals of increase, decrease, and then you try to find your local max and mins. Step 3, you analyze the second derivative. So you find the partition numbers for that. Where is the second derivative 0 or undefined? You make your sign chart, and then you can find where it's concave up, concave down, and find your inflection points. And then finally, step 4, you can locate intercepts, maxima, minima, draw in your inflection points, and then you just use all the information from the original function, the first derivative and the second derivative, and then you can draw a pretty darn good graph as long as you do your scaling pretty well. Okay, so for example 4, we'll start off with, on the test 2, I don't think I'm going to make you do a full graphing analyzation. We'll see, maybe I'll have you do one at most. But you might have seen this on the homework already, right? There's problems on the homework where they just give you all the information about the first and second derivative, and then you go sketch a graph. Generally, I like to do that. So there might be a question where, here's a function, what are the intervals of increase, decrease, what are the intervals of concavity and inflection points. But I don't know yet if I'm going to make you go through a full curve sketching problem on the test. Certainly on the homework, though. So we're going to follow that strategy, and we're going to sketch a graph of f of x equals x to the 4th plus 4x cubed. Okay. So step 1. So the domain of this function, it's a polynomial, so the domain is all real numbers. And then we'll do x-intercepts, and we'll do the y-intercept. I think the y-intercept you can see pretty easily. The y-intercept is the value of the function when x is equal to 0. When you plug in 0 for x, the output is, 0 to the 4th plus 4 times 0 cubed. So your y-intercept would be 0. So 0, the origin is a point on the graph. And for the x-intercepts, you take the function and you set it equal to 0. So the x-intercepts, the y-coordinate is 0. You have to figure out what the x-coordinates are. So I think we can factor out an x cubed. And we'll get x cubed times x plus 4 equals 0. So the x-intercepts are Well, the origin, I guess, right? The origin's going to be both an x and a y-intercept because you're crossing both axes. So that's what I get by setting, well, should I be careful? This means x cubed is equal to 0 or x plus 4 equals 0. So x cubed equals 0 is going to give you an x-intercept of 0, 0. And then x plus 4 equals 0 is going to give you an x-intercept of minus 4 comma 0. Okay. Give me a break. Give me a second. I gotta just. Oh no. This isn't good. Okay, so the video might cut off at this step. So when I make the video for tomorrow, I might just go through a couple of these examples again. Just because I've only got 3% battery and I know the video is going to stop. So I might as well just cut it off here.